Today I'm going to present HDFS Erasure Coding. So simply put, it doubles the storage capacity for your cluster. And this talk will explain how it happens. So when the Google file system paper was published over a decade ago, the objective there was to store massive amount of data on a large number of cheap computers. So to achieve that goal, a breakthrough design was to use machine-level replication to protect against machine failures instead of relying on expensive special-purpose hardware. So this works well. The replication mechanism is simple, scalable, and robust. Therefore, it has been inherited by HDFS and other later file systems. But replication has very high storage overhead. For each logical block, it stores 3 identical replicas. That means the storage overhead is 200%. But during normal operations, the secondary replicas are accessed with a much lower probability than the primary replica. Actually, in the storage industry, a well-known technology called Erasure Coding provides reliable storage with a much lower storage overhead. So now I will give a much simplified example. Assume that we want to store 2 bits, 1 and 0, using replication and XOR or exclusive OR coding. With replication, how do you store the 2 bits reliably? You make a copy. So you make a 1 and 0 copy, and that means you're storing 2 actual bits. With XOR coding, you do a calculation of the exclusive OR of 1 and 0, you get 1. So you're storing 1 extra bit. So with the 2 mechanisms, you have the same data durability. With the 2-way replication and the XOR coding, you can lose any 1 bit and you can recover all the original data. But XOR coding has half the storage overhead because you're storing 1 extra bit instead of 2. But as a trade-off, the recovery from storage failure is slower because you have to do the calculation instead of just switching to a replica. Because of the strong durability and high storage efficiency, many companies are recently switching to erasure coding to store a massive amount of data. For example, Facebook has their F4 system. In their paper, they claim that they're storing 65 petabytes of data, of blobs data in erasure coding form. And Windows online storage, they have 1 petabyte of new data for every 1 or 2 days. And they store all sealed data, meaning data that is not actively updated in erasure coding form. And Google File System is an early adopter of erasure coding, although no concrete data has been published, but we know that they're storing a large portion of data in erasure coding form. So in this talk, I will introduce how we implemented erasure coding in HDFS. Here's a roadmap. First, to understand erasure coding, we want to provide a background, including a little bit of the redundancy theory and how erasure coding is supported in distributed storage systems. Followed by that, I will introduce the HDFS erasure coding architecture, including the name node, client, data node changes. And then I will introduce hardware accelerated erasure encoding and decoding calculation. This is a collaboration with Intel engineers. So first, to better understand erasure coding, I want to introduce 2 terms. One is data durability, meaning how many simultaneous storage failures can the mechanism tolerate. And the second term is storage efficiency. That means how much portion of the storage space is used for useful data instead of replicas or for high availability. So based on these two terms, the default HDFS 3-way replication stores 3 identical replicas for each logical block. That means at any given time, you can tolerate 2 storage failures. And that means the data durability is 2. And during normal operations, you're using you're storing 1 useful data replica and 2 redundant data replicas. That means the portion of useful data is 1/3, or around 33%. So this is the XOR operation, or exclusive OR. This is a table of how XOR is calculated. So given 2 bits 0 and 0, you get 0. So basically, if the 2 input bits are the same, the output is 0. If the 2 input bits are different, the output is 1. That means if you lose 1 bit, you can always recover by doing the XOR calculation again. For example, given the 2 bits 0 and 1, if you lose the 1, you can use the XOR bit to recover the 1. So that means data durability is 1. And in normal operation, you're using 2 bits of space to store useful data and 1 bit of space to store redundant data. That means the storage efficiency is 2/3, or 67%. So there are more advanced forms of erasure coding. The most popular one is Reed-Solomon coding. So Reed-Solomon coding it uses advanced linear algebra calculations. For each input data segment, it uses a matrix, generation matrix, or GT, to multiply that input data segment to get a code word segment, which is longer than the data segment. That means if you lose, so in this example, the data segment has 4 units, and the code word segment has 6 units. That means if you lose any 2 units in the code word, you can always recover. That means the data durability is 2, and storage efficiency is 4/6. 4 is the number of units storing useful data, and 6 is the length of the code word. So from this particular example, Reed-Solomon coding is combining the advantages of the 2 previous forms. It has the same data durability as three-way replication, and it has the same storage efficiency as a simple XOR coding. And more importantly, it is very flexible. You can control the size of the data code word, and you can control the size of the data segment and the code word segment, or the number of parity units. So in summary, so if you have a single replica, the data durability is 0. You cannot tolerate any storage failure. And storage efficiency is 100%. If you have three-way replication, which is a default in HDFS and many other file systems, then data durability is 2. You can tolerate 2 failures, and storage efficiency is 1/3. If you have XOR, but instead of having like 2 input bits, as in our example, if you have a longer input array, like if you have 6 input bits, and you calculate the XOR of all the 6 bits, then you can still tolerate 1 failure. Data durability is 1. But you're storing 7 useful bits using 8 bits of space. That means the storage efficiency is 86%. If you use Reed-Solomon with 6 data units and 3 parity units, then you can tolerate 3 failures. Data durability is 3, and efficiency is 67%. Reed-Solomon with 10 data units and 4 parity units, data durability is 4, and storage efficiency is 71%. So it's clear that erasure coding, in part, and especially Reed-Solomon coding, has pretty significant advantage over replication in terms of storage efficiency. And how to leverage that in distributed storage systems. To understand that point, we first need to understand how files are stored in a distributed storage system. So to manage potentially very large files, distributed storage systems usually divide a file into fixed size chunks. Those are called logical file blocks. In this example, the first block has 128 megabytes, and this is a default block size in HDFS. The second block, and all the way to the 6 blocks. So to store those logical blocks, we need to map those logical blocks to storage blocks, which are stored on storage servers. The most simple mapping between logical and storage block is called contiguous mapping. So for each logical block, we have a one-to-one mapping to a storage block. So the first logical block becomes the first storage block on the first data node or storage server. The second one, and so on and so forth. And after creating a full stripe of storage blocks, we generate parity blocks. So some storage systems use this layout, including the current HDFS. So using this contiguous layout, the data locality is very good. Without any network access, you can access large amount of data contiguously. For example, if your database query is within the first 128 megabyte, you can do purely local I/O. But in the context of erasure coding, a big disadvantage is that this contiguous layout is not able to handle small files very well. In order to save any space, you need to accumulate an entire stripe of big blocks. In this example, it's 6 multiplied by 128 megabyte. It's over 700 megabytes. So if a cluster has a lot of small files, basically under this layout, you cannot save much space using erasure coding. So a second layout is called striping. So basically, it divides each logical block into much smaller units and divide those smaller units onto data nodes in a round-robin fashion. For example, the first small unit with 1 megabyte size is sent to the first storage block, and the second one to the second storage block. After you accumulate a full stripe of those striping units, in this case, it's only 6 megabytes of space, you can generate the parity data. And then the distribution goes round-robin again. So this striped layout is much better in handling small files. And another benefit is that by doing I/O in parallel to different storage servers, you're leveraging the disk spindles in parallel. So in particular, if your cluster has high-end networking, and that means disk is relatively slow compared to network, then this has a big advantage. You're using multiple disks in parallel, and you're fully utilizing the network bandwidth at the writing client. But the disadvantage is that under this layout, the data locality is not as good as contiguous. Without any network access, you can only access, for example, the first 1 megabyte of data. It's very likely that one record is split among multiple striping units. So basically, there are non-trivial trade-offs between striping and contiguous, and between replication and erasure coding. So we have 2 orthogonal dimensions, and different existing systems use different combinations. For example, Facebook's F4, as we introduced, stores 65 petabytes of data. That one is using erasure coding on contiguous layout. When it detects that data is no longer updated, it will accumulate the data and do erasure coding and delete the replicas from replication. And the Windows Online Storage uses the same technology. And for example, currently HDFS is using replication on contiguous block layout. And there are many other systems using striping layout. For example, the Comcast file system, from which we borrowed a lot of design concepts. It supports both erasure coding on striping layout and replication on contiguous layout. And the Ceph storage system very recently added erasure coding support on striping layout. Before that, their storage schema is a replication on striping layout. So back to our roadmap. After the background, I want to introduce how we brought the erasure coding feature into HDFS. So the first question we face is that which block layout we choose to implement erasure coding. So from the previous introduction, we know that the biggest advantage of a striping layout is to handle is better handling of small files, and biggest advantage of the contiguous layout is the good data locality, which is compatible with locality-sensitive applications like MapReduce, for example. To have a better sense of the production clusters, we selected a set of production clusters and did a profiling study. So basically, we grabbed the file system image from each cluster, and we categorized each file in the cluster into 3 types. The first type is small file. those are files that are smaller than a single HDFS block, which is 128 megabyte. And the second type is medium file. It is larger than a block, but not large enough to form a erasure coding group. If we use the popular 6+3 erasure coding schema, that means medium files are larger than 1 block and smaller than 6 blocks. And then there are large blocks which where a single large file can form an erasure coding group of 6 blocks. So the first cluster, in the first cluster, we can see that only less than 2% of files are in the large file category based on file count. But those top 2% files occupy over 65% of space. This reminds us of the US income groups. But this doesn't represent all the clusters. In the second cluster, we can see that still only top 2% of file are in the large file category, but they only occupy about 40% of space. And finally, in the third cluster, large files are negligible in both file counts and storage consumption. So that tells us that in all cases, if we ignore small files and we only want to save for large files, then the saving from erasure coding will be significantly lower. Even in the first cluster, if we only apply erasure coding on the contiguous layout, then we're only saving for the 65% of space usage. And in some other clusters, there will be no saving at all if we do contiguous layout. For example, the third cluster. So that motivates us to face the project. That motivates us to assign the phase 1 of the project to be erasure coding on striping layout. And based on that, we want to support the transition between the current HDFS, which is replication on contiguous layout, to erasure coding on striping layout and back. And in phase 2 of our work, we do want to support erasure coding on contiguous layout, so it works better with locality-sensitive applications. So the striping layout with replication, we haven't decided whether to pursue that direction because currently we don't see a clear need for that combination. So based on this decision, we made changes to both the name node and HDFS client and HDFS data node. I will introduce these architectural changes starting from the name node. On the name node, the most significant change is to generalize the block concept. Because HDFS, from the very beginning, it is based on the concept that there's a simple one-to-one mapping from a logical block to a storage block. To generalize that, given a certain file, HDFS is cutting it into logical blocks, each with a fixed size. Currently, default is 128 megabytes. Based on that, we further cut each logical block into what we call the cells. The cells have a much smaller size than block. In our default setting, it is 64 kilobytes. So we cut each logical block into much smaller cells, and we do the round-robin assignment of cells to storage blocks. In this particular example, the file foo, it has 2 logical blocks, and it has 13 cells. And based on the round-robin assignment, we have 6 storage blocks in total. The first logical block has 3 storage blocks, and the second logical block has 3 logical blocks as well. So that causes another problem. So right now, we're having much more storage blocks than logical blocks. That is causing additional overhead to the name node because HDFS is a single master or single name node architecture, and it is based on JVM. So increasing the memory usage will cause potential garbage collection overhead and so forth. So to handle this problem, we introduced a new hierarchical naming protocol. So simply put, the name node block manager only tracks each logical block. And we name the storage blocks in such a way that whenever receiving a block report, the name node can parse the received block report and interpret the block group ID. To give a little more details, so traditionally HDFS block ID is only a long type integer. And right now we're dividing that block ID into 3 sections. The first section is only 1 bit. It's a binary flag. It tells us whether this block is in contiguous layout or striped layout. We need that flag because we do plan to support a hybrid configuration in a single cluster. So basically replication versus erasure coding is not a per cluster setting, it's a per file setting. So we need a flag to indicate whether this block is replication or erasure coding. And then if it's an erasure coding block, the second section is a block group ID. That's logical block ID. So the third section indicates the index of the storage block in the block group. In our example, the logical block 0, it has storage block 0, 1, 2. So the block group ID will be 0. And for example, if a data node is storing storage block 1, then the index is 1. So the data node will send block report to name node. Name node, after receiving the block report, will parse the block ID and track the status under the correct entry in the block management module under the entire logical block. So on the client side, on the client side, basically we need to change it to support doing parallel I/O to multiple storage servers. And from an engineering point of view, this is actually the most challenging and interesting part. I'll introduce a writing pipeline first. So basically the HDFS client will take input queue of packets and distribute it to multiple what we call the streamers. Each streamer corresponds to one data node. It's responsible for writing the data in its own queue to its data node. This is a very simple producer-consumer model. So the client is responsible for distributing the chunks, and streamer is responsible for writing the chunk to the storage server. So the most interesting part is that each streamer can fail. And we need to do failure handling. And the failure handling of different streamers can interleave to make things more challenging. After filling out the entire storage, after filling out the entire logical block, we need to allocate the next logical block, which means we need to allocate the next set of storage servers for each streamer. So that's why that's the reason we developed a coordinator module to coordinate the update events from all the streamers. More technical details can be checked out from the Jira. So on the reading side, things are simpler. So still, we have multiple readers to read data from storage servers in parallel. And initially, we only read the requested data. And if there's any failure reading the requested data, we always trigger an entire full stripe read. We read the original data, we read the parity data, and we use erasure coding calculation to recover the lost data. So on the data node, we run a reconstruction worker, which we call the erasure coding worker. So this is the purpose of the erasure coding worker is to recover data in the background even before they are requested. So this is very important to avoid delay on the critical data access path, especially if in a erasure coding group, if the original data is lost, then if a client is reading the data, there will be a long delay. If the parity data is lost, the consequence is less severe. So our data node reconstruction process is integrated with the replication monitor on the HDFS name node. Currently, HDFS name node runs a replication monitor to periodically scan all the stored block and discover under-replicated block. So we basically extend this logic to also handle under-protected erasure coding blocks. So the most interesting part is to design new priority algorithms. For example, if a three-way replication block is losing one replica, and an erasure coding block is losing two storage blocks, but one original data and one parity data. How do you compare the priority of repairing these two scenarios? And and the replication monitor module will rank all the recovery tasks and send them to the data node. And we run a erasure coding worker component on the data node, which upon receiving the command will contact other data nodes to grab all the needed data, do the calculation, and push out the recovered data to the final destination. So finally, I want to introduce how we accelerate the erasure coding calculation. So basically, we developed three erasure coding arithmetic calculation libraries. The first one is a legacy coder. It is from Facebook's old HDFS Read project, if you are aware of it. It was initiated as an HDFS project, but right now it's used internally in Facebook. It's a pure Java coder. And so initially, we took that coder, and then we did code optimization to have an optimized pure Java coder. And then we introduced a native coder with Intel's Intelligent Storage Acceleration Library, or ISAL. That library contains both C code, native code, and assembly code, which leverages Intel's latest CPU technology to do matrix multiplication much faster than without. So I will introduce the results later, but the takeaway is that if you do have the right CPU model, then you definitely should use a native coder. Otherwise, you can use a pure Java coder. So some micro benchmark results. We compare the legacy HDFS read coder, the new Java coder, and the native coder. So we can see in both encoding and decoding, the native coder is much faster. It's about 20 times faster than the legacy coder and native Java coder. Because of that, in actual HDFS I/O, the bottleneck is no longer on the arithmetic calculation. The bottleneck comes back to the disk I/O and network I/O. So these results show how it shows HDFS read and write throughput with different coder and different technologies. Because we also compare with the original three-way replication, which is a bar to the far left. Again, we can see that the native coder is much faster than the Java coders, and that caused the read and write to be much faster. It's also interesting to observe that in both reading and writing, if you use erasure coding with the native coder, it's actually much faster than the three-way replication. This is because this micro benchmark is pure sequential I/O. A single client is doing I/O to a set of data nodes. Under the current erasure coding design, we're doing striped parallel I/O. The client is writing the first 64 kilobyte to server 1, second 64 kilobyte to server 2. So the network bandwidth is fully leveraged. In the contrast, under three-way replication, you're always writing big chunk of data to the first storage server, which in most cases is a local storage server. So you're only using one disk at any given time. So in conclusion, erasure coding expands the effective storage capacity by, it's not by 50, it's by 100% actually. It's cutting the storage overhead by 50%. In phase 1, we implemented erasure coding in striped block layout, and we do plan to support the contiguous layout in phase 2. So a little introduction to the upstream effort. The project has been tracked on the Apache Jira HDFS 7285. The design was finalized November last year. The development started January this year. In total, it has 218 commits, about 25,000 lines of code of change. It's a very broad collaboration between Cloudera, Intel, Hortonworks, Huawei, and Yahoo Japan. The phase 2 will support contiguous block layout for better locality. And I do want to acknowledge the great efforts from our contributors. And so actually, today morning we just merged the feature branch to Apache Hadoop trunk. So with that, I'd like to take questions. Oh, yeah, you can use that one.
My question is about benchmark, and you did benchmark with two data skills with read, right?
Yeah, two data nodes are queued. Yeah.
Why you queue two data nodes?
Yeah, because in the reading benchmark, if you don't queue any data node, then no calculation is involved. In order to test the performance of the arithmetic calculation libraries, we have to queue a data node to test the performance of recovering from storage failure. Sorry, can I say it again? Federation. Okay, the question is how is this related to HDFS federation? I would say they are mostly orthogonal. In each federated HDFS instance namespace, you can use erasure coding. Actually, erasure coding is a per file configuration. You can configure this file to be 6+3 coding, the next one's 10+4 coding. And yeah, the configuration can be made independently from namespace to another namespace.
What's the impact for previous customers?
For what customers?
Upgrading to the new version?
Upgrade. So the question is how does this impact upgrade? So we do handle, the only challenging part is that in some old HDFS versions, block IDs are allocated randomly, and then we change to sequential block ID. And we do have logic to handle that. So if you have an old HDFS cluster, you upgrade to the current version, then we do correctly handle the existing blocks. And when you create new blocks, you can choose whether to create in erasure coding form or replication.
Have you heard from Cloudera and Workworks when this might make it into a release?
I don't have too much detail on that. Certainly not on Hortonworks, but on Cloudera, I don't have a clear idea. But upstream is scheduled for 3.0. So that's a very good question. So the question is how many block is required to save space for erasure coding. If you use the striping layout, let me go back. So if you use, for example, 6+3 coding, that means 6 original units and 3 parity units, then you need 6 units for a file. So if, currently our default unit size is 64 kilobyte. So that means a little under megabyte. If your file is around 1 megabyte of space, then it can be used on erasure coding to save space.
And then 6 blocks, not 9?
Not 9, because we generate the last 3. Your file doesn't have to have the 3. The parity, yeah. 3 is just a parity.
That's stored as well.
Oh, it's stored. Oh, the storage, yeah, you do need to use 9 units of storage space. Right. But your logical file has to have 6 units of logical size.
Right.
Yeah.
So block 1, block 2, block 3, all the way up to 6 blocks. And then to write the parity, would that go into a 7th block?
Yeah, that's, no, it would be 9 because, yeah, yeah.
It's pretty much we talked about decline Or
Yeah.
does it depending upon which kernels has to belong to what streams?
So you're talking about the writing pipeline?
Writing or reading?
Right. In writing,
Reading.
you always ask for, so before starting writing a block, you always ask a name node to allocate the data nodes. And then each streamer is assigned a data node.
Or the reading part?
Reading block is the same. Let me go to that part. It's too slow. Okay. Any other questions?
So, let's do an example to a rack awareness, or does that not?
It's a very good question. I didn't mention rack awareness. Actually, so ideally, we do want to we do want the different storage blocks to reside on different racks, so that you can tolerate rack failures. But it's not always easy because with, for example, the default 6+3 coding, to achieve this ideal configuration, you need 9 racks, which is a high requirement on medium-sized cluster. So we do require, at the minimum, you have the enough number of servers, and ideally, you should have the enough number of racks. And a more interesting optimization is to sacrifice some rack fault tolerance in favor of recovery performance, because if you have like a nearby storage block, then in recovery, it's much faster to grab the data and do calculation. So yeah, we do consider both scenarios.
Does it work when you have the balancer running the HDFS and with tiered storage?
Uh-huh.
HDFS? Or is what work
Yeah, so balancer, it will try to balance the storage usage on different data nodes, and we did extend balancer to consider striped blocks. So basically, we want to avoid the case where you originally placed 2 storage blocks on different racks and balancer moving them together. We still want to maintain the node level and rack level fault tolerance. This is the main extension to balancer. For HSM, this is a follow-on task. We haven't done too much optimization for HSM.
For reading, you mentioned you're gonna have to ship around some data on the network.
Mhm.
So if I'm reading the first part, do I need to ship the parity to that node in order to read?
So the question is, in reading, do we need to read parity from remote? The answer is, if there's no failure, then we don't need to. If it's a regular read, we just read data just from the data node containing the data. If there's any failure, we trigger a full stripe read. That includes both your pure original data and the parity data. So yeah, that's a key trade-off between replication and the erasure coding. For erasure coding, the data recovery will be slower. Basically, you're reading many data units from the network, and the client needs to do the calculation locally. That's why the data node background recovery is very important.
How much more CPU intensive is erasure coding as opposed to what we have right now, assuming there's no ISA support?
So yeah, this is a very good question. It's about the not only the performance, but also the overhead to CPU workload that erasure coding costs. I don't have the concrete number of like CPU usage percentage, but in our experiment, we do observe the CPU usage was pretty high without Intel library. With Intel library, we're trying to, because currently we only do pure I/O macro benchmark. What we are working on now is to run erasure coding together with other CPU-intensive workloads, such as Spark, to observe the performance. The results are not, we're working on the experiments. Any other questions? Okay, thanks everyone. So one last point. Many people asked what the erasure in erasure coding means, and my response is don't try to understand that. The erasure is from a historical context. So the easiest thing is just to remember erasure coding is a type of error correction coding. So I think actually we should just call error correction coding in HDFS. All right, thank you everyone.